for the first time, so let me go over just a few things that we talked about before and tell you where to get the rest of the information. Okay, first, I don't have Blackboard set up yet. Okay, still, what we're doing now is trying to get spring and summer schedules set, and they are a mess. So I've been trying to work on that. I haven't had any time to work on Blackboard. So, okay, I'll talk about tomorrow, but there's not much chance I'm going to get very much time tomorrow to work on it either. But I'll get to that in a minute. So for those who are new here, what I did set up is that in Blackboard, let me explain what will happen. I hope all of you are familiar with it. You know, when you get to this class in Blackboard, there's a whole series of tabs over here on the instructor side that bright blue, kind of that color blue. Now, about the second or third one, somewhere in there is one that says instructor information or something like that. I don't have it set up yet, but I'm sorry, the syllabus will be there. I think that's the first one. Syllabus. I don't have that corrected yet, but I will put it there when I do get it corrected. Then it's instructor information, which is right shortly after that, and maybe the next slide or the next one or two tabs. And I'll put my locator card there. Okay? Then on down the ways here, depending on what size screen you have, there's one that says class handouts and more. Okay? Now, ultimately, that will have your PowerPoint shows in it and your research paper instructions in it. And then right now, all that's in there is the YouTube video link.
What you saw?
The YouTube
No. What?
class handouts and more.
Okay, it wasn't in there a while ago.
Okay. How long ago?
Oh, this morning.
No, it wasn't in there this morning. I was in class this morning. I put it in there this afternoon. Okay. So, all right. So anyway, that will be there. Now, when you go to see that, there's a whole bunch of videos. Now, obviously, we haven't had a whole bunch of videos. Well, here's what I do and why I do it. I've taught this course before several times using that. But I leave the last videos there because every now and then, it doesn't happen often, but every now and then, either our system will go down, Blackboard goes down, Screencast-O-Matic goes down, or YouTube, the link, something will happen, and I can't save a class to it. So I'll just teach the class using the projector, but it won't be saved to YouTube. So the last time I taught the class, approximately the same stuff will have been covered, and that will be there. So all the previous classes there now, except for the first day, which is syllabus. Now, YouTube, Screencast-O-Matic and YouTube always loads from the bottom. So the stuff you see at the top is all last time I taught it, which I think was this past summer. And then the very last entry there, that will be the one, and it says syllabus. So we did a lot more than syllabus, but I just had to give it a name. So it's syllabus. We talked about the syllabus, so even though the syllabus is in the other part of Blackboard, it's there. Not up to date yet, and I'll talk about you'll hear me say which parts I'm going to change. Okay? And then we talked about the research paper instruction. There were a few changes to be made there. As soon as I get those done, I'll put those out there as well. So you can still see and hear everything about the research paper instructions. Then my locator card, I put it there, but there were a few changes to be made, so when I make them, I'll put it in Blackboard. But you can still see it and hear what the changes are. And then we talked safety, 3 areas of safety, so you really should listen to those. And then we started on Chapter 1. And we got most of Chapter 1 covered, not all, most of it covered. And that will be, we'll finish Chapter 1 today. We'll do the lab for Chapter 1 today. Well, okay, back up. We'll finish Chapter 1 today and get started on Chapter 2 today. And then the last 2 hours of today, we'll stop wherever we are in Chapter 2 and go to the lab and do the Chapter 1 lab. All right. Next time we meet, next Tuesday, we will continue in Chapter 2. Probably won't finish it. It's a pretty long chapter. But we probably will get far enough to have a lab. So we'll have 2 hours of theory or whatever you want to call it, PowerPoint, that kind of stuff in the book. Then 2 hours of lab for the first lab in chapter 2. And then the last 30 minutes, we'll have the test on chapter 1. Okay. Now, I said this before, but let me go and say it again. The lab for chapter 1, for some reason, is the longest, most diverse, intricate lab of any of the labs we'll do all term. So don't get, when you do today's lab, say, goodness, do we got to go through that every time? No, you don't, okay? But this one will be the longest and the most involved, okay? The test we'll do on Tuesday from chapter 1 is the most quantitative of all the tests you'll do. Most of them will be more multiple choice and just a few calculations and maybe a few fill in the blanks, okay? This one only has a few multiple choice, mostly calculations, and several more fill in the blanks. So quite a bit different from what the rest of the tests will be. Okay. Anything else we need to discuss? Any questions? Either people that were here or weren't here, if you have any things you're uncertain about. So definitely, before you come to class on Tuesday, watch that YouTube video, because a lot of what's going to be covered on the test was in that part, not necessarily this part. All right. Now, this next part is just sort of a temporary thing. Normally on Fridays, I have office hours on the Birmingham West campus from 8 to 12. Okay? But because I had a doctor's appointment last Tuesday, I missed my whole trig class. You know, I was between the blood work and the doctor's appointment. No way I was there the whole time. Okay, so we are making up that class on this campus tomorrow morning, 9 to 10:15. Okay, so if you're going to try to get in touch with me during my office hours tomorrow, don't try between 9 and 10:15. Now, before 9. I hope to be on this campus, but when I talk with I forgot to talk to college today. I'll talk with him in the morning, my supervisor, and if he wants me there, I can swing by there on my way in. If he wants me there in the latter part, I'll swing by on my way home, or I'll go over there, whatever it takes. So I can't tell you for sure where I'll be before 9 or after 10:15. I hope to be on this campus, but I may have to go to the Birmingham West campus. Most Fridays, it will be Birmingham West. Tomorrow is sort of exception. The only other modest change to my office hours, even though I don't put this on the list, I'm usually here before 8 o'clock in the morning, but my first class doesn't start until 8:30. But Tuesday's class that just passed, I had to end it 45 minutes early to get to the appointment, okay? So Tuesday we came in early and started the class at 8:15 rather than 8:30. So we got 15 minutes done then. We did 15 more minutes today, 8:15, and then on Tuesday we'll start at 8:15. So you won't be able to catch me in my office between 8:15 and 8:30 like normal, because I'll be in class. In fact, I'll leave to go to class considerably before 8:15. So those are the only modifications that I have from what will be posted as my office hours. All right, any questions? Okay. Now the first part of this chapter was a bit more quantitative, even though it had a lot of qualitative stuff in it. From here on, it's almost totally qualitative with hardly anything quantitative. Okay? So this is sort of that nebulous stuff they usually have at the beginning of a science course. And it's all good and it's all true, and we're going to follow up on some of this too. Now, even though science, you might say, has been around since the creation of the universe, because that's all involved science, mankind's understanding of science only began about 300 years ago. Not that people hadn't thought about science, but it wasn't really science back then. It was ideas. It was just thinking through things. Okay? Those were the ancient natural philosophers. They thought about things and said, it looks like it's this way. Okay? That's not science. It's the beginning of science, but it's not science. 300 years ago, Galileo was I guess he started off as a natural philosopher in Italy, but he did things very differently from what everybody else had done before. Okay? And the year he died, Newton was born. Isaac Newton. Same year. It's sort of like a tag team, on the way up and down, but not really. But anyway, Newton was born in England, and he continued Galileo's pursuit of science. In fact, improved on it greatly. Now, we'll get to what that change was a little bit later. The additional component here is understanding, not just thinking through issues and looking at it and observing it, but actually basing your understanding on experimental evidence. Galileo was the first one to say, okay, if this is true, then if I do this and this and this, these should be the results. If he didn't get those results, his assumptions were wrong. Okay? That's what Galileo introduced that had not been before. We had had centuries of great thinkers, okay? Maybe even a millennia of great thinkers that thought about science, though it wasn't science then, and came up with ideas, but the trouble is they stopped with that. Okay? Now we're going to several times come back to this concept, these concepts that Galileo and Newton introduced. In fact, they are the star players in the next two chapters, in fact. So here's the scientific method. Basically, as developed by Galileo and improved on by Newton, and then continued to be improved on over the years. Starting just like the ancient philosophers did, observing some aspect of nature. Okay? Continuing just like they did, propose an explanation for those things that were observed, just like the ancients did. Now, here's what Galileo and then later Newton began deviating a little bit. They used the explanation they developed here to make predictions. Well, if I do this, then this should happen, right? If all these things were true. So then they start testing those predictions with experiments or more observations to see if indeed they are true. If they're not, then go back and produce a new explanation. Return to number 3. And keep doing that. In fact, most of science is a continual effort in this way. My wife is a researcher at UAB. She studies a disease called cytomegalovirus, CMV. It causes hearing loss in young children and also several other sequelae, you might say, but that's the most predominant one. Okay? She's in a group, and they've been studying this disease and how to detect it, how to follow it, how to manage it, what to do with it, and they're constantly going through this kind of cycle. They'll say, well, perhaps this. They'll do experiments on it, and they say, well, no, that won't do too well. For instance, they were trying to detect it with cord blood spots, okay, or with saliva, or other things like this, so it's less invasive on the child when the child is born to test for it. They test these things and may or may not come up with an improvement. But that cycle just goes over and over and over. Can I get your name, please? Second. One more time.
Raina.
R?
E-N-A.
Okay.
Radio.
Okay. R? Spell it one more time.
R-E-N-A.
Oh! R-E-N-A.
Are you?
That you?
Yeah, that's me.
Okay.
Yeah.
All right.
Long time.
Long time.
Yeah.
Okay. All right. And you still go by Renee? Raina.
Yeah.
Okay, Raina. Okay. Let me get that pronounced. Okay. All right. And I'm gonna mark you. Okay, we're still missing Sarah, Clinton, Demetric, Justin, and Tyler Scott. Okay. All right, good deal. Okay. Now, when I was doing research, mostly at the University of Georgia, when I was doing my master's program there, I was in a group, and we were studying a variety of things. I was in agronomy then, and studying a variety of things that improved crop performance and stuff. So we were trying to determine how much effect adding limestone had to certain soils and how to improve or change growth outcomes. Well, we would try various levels, okay? And I think we'll get to this on another slide, so hold on a minute. I think that's better. Yeah, here we go. Here's an example. I'll come back to that in a minute. And this is sort of a strange one, but one example. What are atoms made of? Okay? Wait a minute. You may have learned in science or chemistry sometime a long time ago, I don't know how long it goes, how old you are, but that the atom was the smallest particle in nature. Okay? But we know today that's not quite true. So what are atoms made of? Well, we know that there are negative particles that fly around a positive nucleus. Okay? And those negative particles are called electrons, and that nucleus has other particles inside of it. Now, over time, they've tried many different things, including colliding two atoms at really high speeds to see what comes out of it, okay? And they'll see these electrons fly off, and they'll see either the nuclei or pieces of the nuclei come out. And by studying those pieces and stuff, they can find out what constitutes an atom. So colliding two atoms yielded electrons. Later they found protons. Later they found neutrons. Okay? Now, just to give you an idea, electrons, as I said, are negatively charged particles here. Okay? Protons are positively charged particles. Okay? Neutrons are neutral, no charge. Okay? They were hard to detect because they're small and had no charge to let you know they were there. They just knew there was some mass there they hadn't accounted for. So, what they came up with is atoms are made of electrons orbiting a nucleus made of protons and neutrons. Now, that wasn't the original model. The original model, actually they call it the plum pudding model, that you had the pudding and raisins scattered around in the pudding, and they thought that was the electrons, and the pudding was basically your nuclei. Well, they found out that wasn't true. A guy named, I'm blank on his name now, came up with an experiment, and he found out that nope, most of the, he fired alpha particles through a gold sheet, expecting most of them to get bounced back at him, okay? Most of them went right through with nothing bothering them at all. That let them know that most of the volume of atoms was empty space. The nucleus had most of the mass, in fact, almost all the mass, but it was in a tiny, tiny, tiny volume. The electron cloud, which was almost no mass at all, took up most of the volume. So therefore, most of the atom was empty space with a huge, very small, but huge, massive nucleus in the middle. So different experiments had them go back and go through the model again and again, improving the models. Okay? So once they discovered that, well, let's collide at higher energy and see what else. Well, now they know that there are other particles. There are things called positrons. There are things called neutrinos. There are all sorts of things inside an atom that sometimes we don't even know what they do for sure, but we know that they're there. Okay? or at least they're a product of the collision somehow. Okay. Now, the general activities then, starting just like the ancients did, making observations, making lots and lots of observations. For instance, say in my wife's research, people observed that kids with CMV tended to have more hearing loss than kids without CMV. So they started doing all these studies, and over the time, they said, you know, there has to be a link here. So they developed, or at least came up with some ideas to explain this. They tested those explanations, and sure enough, found out that not only that CMV infection can cause hearing loss, but that most of the childhood hearing loss is probably associated with CMV and not something else. Okay, for years they just said unknown, unknown. They may have had a high fever. They may have done, yeah. Now they know that most of that was in CMV. Actually, some of that research she's been mostly involved with and been the lead investigator on much of that. Now,
What do you call that? COP?
oh, CMV, cytomegalovirus. You don't need to know that for the course. That's just a disease that.
I'm just genuinely interested, but
Yeah.
I can't hear either.
Okay, yeah, I can't either, and she suspects I probably had it too when I was a
I
child.
don't know.
Yeah.
I think mine come from loud noises.
Yeah, and I know
No, I know it is.
mine progressed through that because I was in the Navy and on the aircraft carrier. I was a gunnery officer, so I mean, all sorts of. Huh? I couldn't hear.
M16. M16.
Oh, no, I never had to fire any of those much. So I imagine they're rather loud too. But I also grew up on a farm, and we used chainsaws a lot and lots of loud equipment. So I had plenty of things to damage. Yeah, plenty of opportunities to damage my ears. But she suspects that I probably had CMV hearing loss to begin with that just made it worse. Okay. Here's what I was trying to get to. Okay. How do they do these investigations? How do they pursue these explanations? Well, one way is this way. You come up with a hypothesis. Okay. That's where I was going to introduce the plots of growing corn that we did in near Athens, Georgia, when I was on my master's program. We suspected that the acidity of the soil was impeding the growth of corn, okay, or other crops as well. So we took plots of land and we tried to get as uniform a type of plot as we could, okay. All the land pretty much the same characteristics, slope, water retention, types of soil, everything else that we could, okay? And we split that plot into so many subplots, okay? And we treated overall the whole plot with the basic stuff, everything identical. And then for the lime, we put so much on this plot, so much on that, and varied it around and took careful notes of where we put what. So the experiment was a recreation of an event, different levels of liming, to test the hypothesis, to see if the lime rate did have something to do with corn growth, as long as all the other things were constant. You know, in other words, all the other factors, all the other nutrients and everything else were the same. That's called a controlled experiment. There were some of those plots that got 0 lime, okay? Now we had tested it before, and that plot, the whole big plot, had the same, or very close to the same pH. So we started with some receiving no lime, others receiving a little bit, others a little bit more, and others something probably in excess, okay? Trying to find what level of liming would grow the best corn. So the control group was the part that we had everything else the same. All the fertility, all the nitrogen, phosphorus, potassium, calcium, sulfur, everything was the same on the control group, but no lyme. Then the experimental group differed from the control group by that one influencing factor, the lyme rate. And that's about when Justin comes in, okay? Anyone else comes in? I called roll. Okay. Now, and then we were able to determine. We gathered the yield, measured it, and sure enough saw that a certain amount of liming improved, and then after a while adding more lime didn't seem to change anything. And I think other studies have shown too much lime may actually block some of the other nutrients. So they did discover, or we and others put together and found out for at least that soil what was the optimal liming rate for that. Okay? But then different soils may need different treatments. Okay? And you can study that through these same type of control experiments. Now my wife, on her study that she did as a doctoral student, she couldn't control, so she did observational studies, and they went through medical records. I mean, she was going through records just all the time of women who delivered children who tested positive for CMV. And when they did so, then she would pick another delivery within a day or two of that same delivery, okay? Same gender of the child, if possible, okay? Same race or nationality of that child, if possible. Same socioeconomic status, if possible. So she controlled for as many of the things as she could, but the one child was born with positive for CMV, the others weren't. And then she studied to see what could have been the thing. And then they followed those children, or maybe this was a later study, over the years and saw which ones came up with hearing loss. And they were able to determine that a huge proportion of hearing loss that had been declared unknown was truly related to the CMV infection. Okay. So again, very similar thing. Her control group were what they call the, they actually call them the controls, the kids without CMV, and the experimental group were those with, and then they tried to study the various factors, things that came into play. Okay. Now, this author sort of gets carried a little bit away with what he calls pseudoscience. Does anyone know what the prefix pseudo means? Say again?
Similar.
In a little bit of a way, perhaps. Does anyone know what a pseudonym is? I'll give you a hint. The nym, we get the word name from. A pseudonym, let's see if I can think of one. This is way back. A. Milne wrote the Winnie the Pooh stories. I don't know if any of you even know Winnie the Pooh. But that wasn't his name. He was a respected doctor or something like this, but he enjoyed writing stories for his son, who Christopher Robin was modeled after. Okay. So he didn't want, and they were so nice and such nice stories, people encouraged him to write them and publish them, but he was embarrassed, he's a big important doctor, to be writing kids' books that he used a false name. That's what pseudonym is, a false name. In some ways, you've probably heard of this author, J.K. Rowling. Okay, what she write? Yeah, she wrote the Harry Potter stories. Okay, the books, the franchise. Okay. Why did she go by J.K.? She didn't want anyone to know she was a woman. Those are her initials, but she wouldn't go by Janet or whatever her name was because she thought she'd be written off. She found out that when she did try to get her books published, she wasn't paying any attention. When she put her name on it, so when she put her initials, they paid more attention because they thought JK sounded like a man, you know. So she got published then, and then later they found out she was a woman. So quite often that kind of stuff has happened. So pseudo means false science. That's almost a contradiction in terms. If it's science, it's not false. If it's false, it's not science, okay? These are misleading and often absurd claims of scientific results. Now, why in the world would someone do that? Well, there are a few reasons that, while not excusable, you can almost understand them. I don't know if you've heard the term publish or perish. If people are up at the doctoral level at these major research institutions, most of the major universities are research institutions. If those professors don't publish, they usually get the boot, okay? And they have to publish a certain amount. Now, my wife has published quite a bit, but she doesn't publish as much as some of the guys do because her papers usually get published in the really good journals, whereas a lot of other people just publish like crazy in little bitty journals. You know, just do a simple little study and publish it. You know, and anyone that'll take it. They get a lot of publications, but they're not in very significant journals, and they really aren't showing very much. She tends to overdo it and follow everything up and make sure it's a groundbreaking, well, not quite, but you know, something like that. So she doesn't publish much, but she's been able to stay on. Okay. So anyway, here are some of the tests to see whether, what I was getting to, so why would someone make up claims? Well, they may work for years on this set of experiments trying to prove something, and then when it's coming time that they need to show some results, all the results are conflicting, and they're not going to get any publications out of it. So some people have actually then turned around and claimed to have discovered things they really can't substantiate. Okay, yeah, and that doesn't. Otherwise, they get 10. Well, when it's discovered, they get 10. So they just hope it's not discovered for a few more years, okay? So anyway, here are some of the tests. Other people just do it for idiocy, okay? The internet is full of this stuff. As I was talking about when I was saying using the internet as a source for your research papers, be very careful. There is people out there who will just make any kind of claim possible. And because it's the internet, no one ever questions, okay? So here are some of the tests. What's the academic and scientific background of the claimant, okay? Has that person got a history of good, reasonable publications? Now that's sort of a catch-22. A new upstart doesn't have that, so do you then neglect everything that he does or she does? No, you can't do that. So what's the academic and scientific background of the claimant? Now here's what in reality happens. If you have something you think is really significant, you try to get someone senior who has a good track record to get on the paper with you. So they won't kick it out because they've never heard of you. If they've heard of that person, then they'll more likely go on the publish. The history of review by scientific peers. Now this is going to show up later too. A lot of the stuff on the internet, a lot of times it's just one person's opinion. Well, in the Navy they used to have a phrase for an opinion. Okay, you've heard it too. Okay. Yeah.
I've also done it.
Yeah, okay. But anyway, we won't get into what that is. Everybody's got one, okay, is what the punchline was. But you know what? Opinions are something. What about when everybody else reviews it? So guess what? When you submit the paper, it goes out to at least 3 different leading scientists, and they review the paper. And usually, especially if it's something that's brand new, sort of groundbreaking type thing, they will send it to a lab and say, do what they say they did, see if you get the same results. And if they do, then they say, yeah, this looks really exciting, then they publish the paper. Otherwise, they hold on to it and say, until they can get confirmatory data, they're not going to publish it. So that's what they mean, a history review by scientific peers that have reviewed it and said, this looks pretty weak here, or this, I'm not sure this is accurate here, so that kind of stuff. It is tough to get published. Okay. Participation in scientific institutions and organizations. Well, that's kind of like this one. In other words, do they go to professional meetings? Do they present the results there? Where they get questioned by their peers? Okay. Are they members of some significant university, national laboratory, something like this, that, or do they have affiliations with them? And then this one's a lot like this one. The claim published in peer-reviewed journal and independently validated by others. That's when they send them to other labs to see if you get the same results. And if you do, then groundbreaking paper, and you get the credit for it, not the people that other. But so this is how we try to avoid the pseudoscience, okay, by those tests. So just reading something in the paper or off the internet means almost nothing, okay? Anyone can write anything they want to. In fact, now a lot of people really love Wikipedia, and generally Wikipedia is pretty good, but there have been some people who get out there and abuse it like crazy and just will put anything down. And if you get enough people believing that anything, then suddenly people think it's true. Yes?
I think I come to the realization last summer course. I didn't know, I thought everything in Wiki was accurate.
Right.
But then I found out, hey, it's just posted by people, it might or might not.
Exactly. Exactly.
And we trying to write papers and using that, we better be careful.
Yeah, very, very
I think
careful.
you probably know the difference.
Yeah, right. I've read many papers that Wikipedia has been the source. I've never used Wikipedia as a source. I've looked up things on Wikipedia just to see who else is out there with it and stuff, but I've never used it as a source for
Well, they
anything.
have, most good sites have references in there.
Exactly, and that
You can go there
and check it out. That's exactly what you do. Okay. Now, when you're dealing with the organization of science, some of these are just words, okay? And some of these words, their definitions almost sound like the same thing. And I'll try to point out when that's true or when there's a little bit of difference in it. So here's the first. There are things called laws and then principles. Very, very similar. In fact, some people argue something needs to be a law when it's called the principle or vice versa. But here's what a law is. It's an important relationship observed to occur time after time after time. Okay? For instance, gravity is an attractive force. You throw something into the air, it's going to fall back down. Okay? Every time. Okay? Unless, of course, you have a really good arm and throw it at such a high velocity it can escape the gravitational field. No one has that kind of arm. You take booster rockets to get an enormous amount of energy to get a spacecraft, a tiny little capsule into space. Enormous amount, okay? Because you have to overcome that gravity, okay? Laws are usually descriptive in nature. And what they mean by that, they're describing something like throw something in the air, it comes back down. That's a description. They're not prescriptive necessarily in that they are projecting something else. They could. Now, this is not me. The guy whose last name was Charles. Charles's law describes the relationship between temperature and pressure in gases. Okay? Now, this is assuming that the volume is held constant. So if you had a constant volume and you increase temperature, what's going to happen to the pressure? The pressure goes up as well. Decrease temperature, the pressure decreases as well. Okay? Now, dumb sort of example of this, when I was living in Nebraska at working on my graduate program there, a lady who went to our church, she and her husband were split. He lived in a city a long way away. Her two kids were growing up without a dad, and she wanted her son to be exposed to some more male influences, so she asked people if they could. I was single, young, and I thought, no, not me. But then when he came out, and he was a really good athlete, came out and was playing on the church softball team, he and I just got along so well, I thought, well, why not? Let's give it a shot. So we started doing some things together. I remember this is in Nebraska, remember? And it was late one fall day. It was a Sunday afternoon, but it was still really cold. And he wanted to shoot some basketball, but he had left the basketball out overnight. And he went to pick it up, and it was pretty soft. He said, man, I must have punctured the basketball. I said, no, put it in the house. He said, why? Just put it in the house, okay? Because the house was warm. And he put it in, and we did something else for a while. I said, well, go get the basketball. He went and got it. It was fully. Why? Because when the temperature dropped, okay, down in the 30s or 40s, the basketball, the pressure was much less. When you put it back in the house where it was 60 or 70, in the upper 60s or 70s, then the pressure was greater without putting any more air in it, okay? That was an example of Charles's law. Now, there's another one. I don't know if y'all want to hear a really way too long, but it's a pretty funny story on, goodness, I can't think of the guy's name now. Boyle's law, okay? Boyle's law relates pressure and volume with temperature held constant. You want to hear the dumb story? I mean, it's true too, or not? Just as soon do? Okay. I was in Navy ROTC when I was in college, and if you're on scholarship, you had to do 3 midshipman cruises. One between your freshman and sophomore year, one between your sophomore and junior year, and one between your junior and senior year. About 6 weeks out of the summer. So I couldn't do classes and stuff, but I was fine with that too. The one between my sophomore and junior years was split into 2 3-week sections. First 3 weeks we went to Little Creek, Virginia for amphibious Navy and Marine training. Okay? And then the next 3 weeks we went to Corpus Christi, Texas, and there we had naval aviation training. Prior to that, I had only been, I'd never been in an airplane in my life, okay? Until they flew us from Little Creek, Virginia to Corpus Christi, Texas in a military transport, which had webbed seats, not anything fancy like you would expect. You face backwards. I still don't know why they did that. And, it was pretty boring. No cabin service or anything else. They may have served lunch, but you just got it in a bag and you ate it. Okay? So that was my first flight ever. And it wasn't bad. No, I wasn't scared of flying or anything. I knew nothing of it. We got there, and we got there late one week, and Monday of the next week, we started our naval aviation training. And they had to have some groups get started first, and then other groups followed for the next 3 weeks. I happened to be in the group that got it first. So with like a morning's worth of orientation and indoctrination, then that afternoon, I was in the front seat of a trainer, which is a little single engine prop job, in the front seat with the instructor in the back seat, and I was supposed to be taking off and doing everything in the flight. Well, it was new to me. Okay. Next day, we had acrobatics. Oh no, the next day we were supposed to be, whereas he was doing most of the stuff the first day, even though he was in the back seat. The next day I was supposed to be doing most of it. No, okay, I did not want to be an aviator, so I didn't do too well that day. Okay, he took over right away when he saw how. That was my third flight ever. Okay, the fourth flight was acrobatics, and he took us up in that little single engine prop and started doing barrel rolls, loop-de-loops, all this kind of stuff. I never wanted to throw up so badly in my life, but I hadn't eaten lunch, so there was nothing to come up. So anyway, it was, I definitely did not want to be an aviator. Okay, farther thing for me. The fourth flight, which is the fifth time I'd ever been in an airplane, that was nice. We were in a 4-engine prop plane. It was a surveillance type plane. It rode like a Cadillac compared to that other little thing with a single engine that was miserable. Okay, and the pilot was a lot of fun. We buzzed the beaches. You know, it was nice. I thought, okay, maybe I could be a pilot. No, I wasn't going to be a pilot. But the fifth flight, which is my 6th time in a plane, the very next day, Friday of that week, they got us on a bus and we rode for about an hour or two, and they split us into the 3 groups. There were going to be general orient. This is our jet hop. The first 4 were propeller-driven planes. This was jets. All the ones that want to be aviators, they were just so fired up to be on the jet hop. So you get to choose general orientation, acrobatics, and if there was opportunity for it, a sea hop. What was a sea hop? Combat hop. This is where they're training the pilot to be a jet pilot, and the instructor was in this aircraft, and the guy being trained with his instructor in the back seat of this one. Well, the back seat was open on this one, and this instructor and the student were going to be having dogfights in the air, not with real weapons, but zooming in, picking, and the computer would tell them where you got to hit or not. And they would exchange position. One would be the aggressor, the other would be the defender, and you did that, and they were doing that. And so that was the combat hop. You were actually in the back seat of the plane that was having a dogfight with another plane, okay, without weapons, thank goodness. General orientation, all the way for me, okay? I didn't want combat hop. I didn't want acrobatics. Just get me. I was picturing it being something like that big 4-engine propeller thing, just a general flight. That's all I needed. Well, some of them were just so eager to get on that combat hop if it was available. Others say, oh, I like the acrobatics before, I'll take that. Well, the chief that was collecting the stuff put A, B, and C. And he handed the list to the other chief, and so the trouble is they didn't identify which was A, B, and C. The first one had A as a general orientation, A is the combat hop, B is the acrobatics, and C is the general orientation. The next chief just assumed C was combat hop and A was general orientation. So my A, who had chosen general orientation, we were shipped out. I was in the back seat of a dogfight, okay? And that was absolutely miserable. I never could, it was a cloudy day, overcast. I could hardly ever see the other plane, period. I didn't know what they were doing. All I knew, we were just doing everything. And I'd look out, and sometimes I'd see the horizon, and it'd be like this, but the ground was up here, and the sky was down here. It was just miserable. And finally, I said, let me just look at the instruments. And in the older aircraft, they had a globe there, and the top half was white, and the bottom half was black. And it had the latitude, longitude lines around it and stuff. And what that was your level flight indicator. And if you were flying level, the equator was flat. If you were at tilt, then it was like this, or whatever. If you're going down, going up, you would see different parts. Well, I decided to look at the altimeter and things. Well, I looked at that, and all I saw was the soft spoke spinning like this. I said, I don't even want to think about what that means. I don't want to go there. So I was trying like crazy to throw up, but every time, when you're in a jet plane, especially when you're taking sudden turns and stuff, they have on they call it a G suit. It's a gravity suit. It's basically a belt here and belts around your calves and thighs and around your waist. And when you start taking G's, which people tend to black out, they automatically inflate, forcing the air, because when you do something like this, all the air rushes to your feet and your head, you get dizzy, and you can lose consciousness. So to keep that from happening, you had the G suits to squeeze on you, and they said when they squeeze, you better push back, otherwise it feels like it's going to cut you in two. So every now and then when I thought I might throw up, then I'd have to push and stuff. I never could have any relief of anything. And it was miserable. Okay. Well, so much for that. Remember the jet jockeys that were wanting like everything to go on the combat hop? They wound up in the general orientation flights. And boy, some of them were furious because they wanted that C hop. And this one in particular, he's a nice guy, quiet little guy, but he wanted so much to be in that. And so when he found out it was general orientation, he sort of pitched a fit. And evidently his instructor pilot that day hadn't been having a very good day. And this little midshipman here going on and on about needing to be in combat hop, wanted to take him back to the base and put him on a combat hop. Too late. I mean, it's all over. You know, the combats went first thing in the morning. That's why I was in that. And it's too late for them to swap with me. So, and the good news was it was early, and I had gone up there before lunch. Well, Greg went with his right after lunch. Fried chicken. Nice, greasy food. And his pilot got so upset with him that he took him on the equivalent of a combat hop. And he twisted and turned, especially general orientation, they did acrobatics you wouldn't believe. And one of those, he just took a dive down here, and at that point, all that fried chicken came back up. So Greg got his barf bag, all aircraft have barf bags, and got it and barfed, and he was too embarrassed to let his pilot know he had thrown up. The pilot was up there, he was back here. So he threw up into his bag and held it really tight, okay? Right at the bottom of this thing, okay? And then he went into a climb. Greg was just holding to make sure none of the fumes got out of this, but wasn't paying attention to it. But at the bottom of the dip, you were at maximum pressure. And as you went up, the pressure decreased big time. And he was holding real tight to his bag to keep the smell from coming out, and he didn't realize the bag was inflating like crazy, okay? Because of Boyle's law, which was at constant temperature, which the aircraft is pretty much constant temperature, as the pressure goes down, the volume goes up. He held on to it, and at some point, pop, and the bag exploded with the puke of former fried chicken all over the cockpit. And the instructor pilot, who was not very happy with him to begin with, what in the world, probably a slightly different language than that, is going on back there? And they said that he had to clean the cockpit with Q-tips, okay? And you can just imagine how the complicated instrument panel, how many things were there, and he had to clean it all. Now, we were sitting in, they were the last ones to come back. We were sitting in the classroom waiting for people to come back. I had my fried chicken lunch, and it was really good, you know. And suddenly, he stopped and said, "What's that?" You know, it was Greg entering the building. Way down the hall, you could smell him from there. His barred flight suit coated. Okay. Anyway, that was the story of Boyle's law as opposed to Charles' law, but you didn't want to hear that. Okay. Anyway, those are laws. Things that happen every time, okay? Now, what's the difference of that and the principles? Not much, okay? Some principles maybe could be called laws, but others maybe should be called laws, could be called principles. So here's what a principle is. It's also descriptive, just like a law is, but it's more specific than the law, okay? Not just a generality that's always true, but something a little more specific. And the difference is largely just how you explain it, one of the extent. There's not always a clear distinction. Some people will call Archimedes' principle regarding buoyancy as a principle. Other people will call it Archimedes' law. Okay? So they're very, very similar in nature. But the principles tend to be a little more specific. One that I think of is Bernoulli's principle. Anyone ever heard of it? Okay. say I've got this piece of paper here. I'm trying to make sure it's pretty flashy. Okay. What would happen if I blow on the bottom of it? Any ideas?
Flutter, make a noise.
Okay, it might. What will it do?
Flutter.
It'll go up. Flutter. Okay, going. Okay, I didn't hear flutter first. Okay. Sure enough, it went up. Now, what if I take the same piece of paper and blow over the top of it? What will it do?
Nothing.
It'll what?
Do nothing. It'll do nothing.
Do nothing. Okay. Any other ideas?
It might go down a little.
Down a little bit. Okay, let's see what happens.
Uh-oh.
Uh-oh. It came up too.
A wing airport.
What's that?
An airplane wing.
You're absolutely right. It's the principle, Bernoulli's principle, says that a fluid, whether it's a liquid or a solid, if you increase its velocity, you decrease its pressure. Okay? Now, sure, I increased the velocity here, but where did it go? It only blew against the paper and made it go up. But when I increased the velocity over the top, because the increased velocity, the pressure was less, it lifted the paper up. And you're absolutely right. That's why a plane can fly. Okay? Now, it's also, I guess you've probably been on the interstate before, and a big old transfer truck going way too fast goes rushing by you. Maybe you just pulled on. What do you feel?
Suction.
Yeah, it's almost sucks you behind it. That's Bernoulli's principle. The increased velocity decreases the pressure, and you're pulled forward. That's also what, any of you, none of you went to Talladega, did you? Right, okay, but you probably watched them before. What do those lesser drivers on a team do? They lead for the first part, don't they? Why? So the big name driver can draft on them, right? And when they draft on them, he's saving his energy, fuel efficient, and that kind of stuff. And then toward the end, he pulls around and you do come better chance of winning the race. Okay? That's Bernoulli's principle. Increase velocity of a fluid, a gas or a liquid, will decrease the velocity, the pressure. Okay. Now, there's other things like theories and models. Okay, laws are seen always to be true. Principles are a little more specific and, but still usually true. But theories are ideas. Okay, remember the hypothesis that we were testing before? You know, you can test a hypothesis until the cows come home. You really never prove a theory. You just add evidence to support the theory, or you contradict it. Okay? It's a broadly based set of working hypotheses that seem to be true. All indications are they true. They're based on considerable experimental support, or otherwise they wouldn't even be called a theory. They form a framework of thought and experiment, but you know, it takes an awful lot of work to say, yes, absolutely, this is true. Okay? I don't mean to bring up anything political here, but the theory of evolution. I don't know where you stand on anything else. Some people treat it as if that is fact. But guess what? How do you test the theory of evolution? You have to start back over with one or two molecules and see if you can make them evolve into something else. And sure, there's lots of evidence hinting that way, but there's no way to prove it. So evolution will always and forever remain a theory. Okay? The Big Bang Theory. No way you can start over and see. It's sort of like a test on a final exam in a physics class. One question, 2 parts. First part, define the universe. Part 2, give 3 examples. Nah, you can't do that. That's the joke. Okay, but it can't be done. A theory is a theory because it's not a fact. It's something you're always trying to test, support, build on, that type of thing. Okay? a framework for further thought, further experiment. And if at some point they finally say, yeah, nothing refutes this, maybe it will become a principle. Most theories will remain a theory. Okay. Models. It's a collection of theories or just ideas intended to represent a physical system. Okay? Now, quite often, you're dealing with things that are either too small or way too big to actually have direct observations, like the Big Bang Theory. Okay? You can't reproduce that because you talk about the entire universe. Okay? You can't do it. Okay? Or if you're trying to model what's going on in those atoms we were talking about. You can't do it. You can't see an atom. You can't get down to measure an atom. You can measure other things. Okay? Now, let's go to that atomic theory. Okay? Long before what we saw earlier about electrons, there was a guy, and his name was John Dalton, and he did a lot in building that atomic theory. And he had observed, and many others had observed over time, that different materials combine always in definite ratios, certain definite proportions. Okay? And John Dalton proposed this. It was a model. He said, let's imagine, for instance, carbon. Think of carbon dioxide, CO2. Okay? Oxygen, pretty much people have known, combine, say, with hydrogen to form water. One oxygen, two hydrogen, H2O, right? Nothing else combines with it. It's happy to be H2O. But then oxygen combines with carbon to be CO2. Okay? In carbon, you can observe other things, like methane is CH4. But everything is these certain proportions. So after a while, he said, look, it's sort of like, now this is his model, it's not, he didn't even think this was true, but he said it's sort of like carbon has 4 hooks on it. Oxygen has 2 hooks. Hydrogen has 1 hook. So oxygen will hook with 2 hydrogens, and it'll be happy. It won't combine with anything else. That's H2O. But carbon and oxygen, 2 hooks on oxygen, 4 hooks on carbon, 2 and 2, you got carbon dioxide. Okay? And sure enough, that was a pretty good model. He knew there probably weren't hooks there, but something that acted like hooks. We know now, basically, they're electron pairs that pair up that way, and that's what his was. But originally, he didn't know about electrons, or that they paired up, or anything else that came with quantum mechanics. Okay? So, it's either for very small or huge regimes that you can't really do anything but model. Okay? My wife's doctoral advisor, every time she came in with some idea, he'd say, what's the biological plausibility of that? Okay, that was his favorite phrase. What's the biological plausibility? Okay, that's a good model, but why should that be true? What is the biology behind it that would make that true? Well, you got to do the same thing. That's my professor with the corn and soybeans or other plots. He had an idea that why these things work, and that's what he based his other experiments on. So sometimes these models are physical models, like the hook or something like that. Other times they've been purely mathematical models. There was a guy named James Clerk Maxwell. Now it's spelled as if it's Clerk, C-L-E-R-K, but he's Scottish. You know the Scottish pronounce things wrong. So it was pronounced Clark, but it was spelled Clerk. He had studied electromagnetic radiation, observed it, and stuff. Didn't have the equipment to measure it really, but he sat down with mathematical ideas and put together Maxwell's laws, 4 Maxwell laws, explaining why he thought electromagnetic radiation did what it did. And boy, his formulas and equations, they're strictly mathematical. They seem to fit. They seem to be quite good. probably a generation and a half later, when finally the technology advanced to such a thing that they had the equipment to measure the stuff. I think it was Heinrich Hertz was able to measure and prove every one of his model ideas showed to be absolutely true. He did it only with formulas and equations, a mathematical model, but he modeled a real physical phenomenon. Impressive guy. Okay. Here's one example of a model. Okay? We're not absolutely sure this is true, but it's a model that fits, and I believe that it probably is true. Now, I don't know if you can see it well. I think you probably can from where you are. I've seen maybe 2 or 3 of these in my lifetime that have been this stark. A rainbow, but then a second rainbow outside of it. Why do sometimes we get a double rainbow? That's the question. And they have come up with some hypotheses or models to explain it. Now, if you think about all the rainbows you've ever seen in your life, whether they're double or single, did you ever notice anything that was common to them?
The colors?
The what? The colors. Okay, you're absolutely right. The colors are always the same, in the same order. Okay? I'll say the colors for you, kinda. Red, orange, yellow, green, blue, indigo, and violet. Now, I can't see those, but I just made them up. What are those? The colors of the visible spectrum. Roy G. Bibb. That's how I came up with that. But those are the colors that are there. Okay? Visible light. Okay? You can take a prism and shine a light through it, and you'll see those colors show up always in the same way. But I was thinking about the rainbow. Where do you see the rainbow? When do you see the rainbow? Second?
After rain.
After rain, that's for sure. Okay? And that is important in the theory and the model we're going to do. Okay? It's after the rain, not before the rain. Which way are you facing? When do you see the rainbow? After the rain. But what time of day? Have you ever seen a rainbow at noon? Yeah.
I never looked at
Every rainbow I can ever recall has been in the afternoon. I think I may have seen a few in the morning, but I don't think I've ever seen one right near the noontime. Maybe, but I don't think so. And here's why. If you've ever noticed where you're looking when you see a rainbow, the sun is always at your back. Always. You never see a rainbow facing the sun. You can't. It doesn't exist. The rainbow is always, you're facing, the sun is right at your back. Okay? The rainbow is always about the same angle. From the center here, wherever the center is, that angle is always the same. And if you do see the double rainbow, the second rainbow, it's always a fixed distance from that. Always. What could account for all these phenomena? Okay? The theory, the model is it's a result of the reflection and refraction of sunlight within the individual raindrops. Wow, what does that mean? Okay? Well, here's the first thing. We're going to model the raindrops as if they're little spheres. Now, you know they're not perfect little spheres because gravity's pulling down and you get this teardrop shaped thing. But the sphere is a pretty good model for it. Okay? Now, if that raindrop was a perfect little sphere, sunlight coming in here is basically going to go straight through. Okay? Sunlight coming in here pretty much is going to go straight through. But there is some place up here where the angle of this surface here is such that when the sunlight hits it, it gets split into a spectrum, just like a prism does. Okay? It does a little bit down here, it'll do more, yeah, but it just gets lost in the sauce there. But at one place that it comes in here, it splits it this way. That's, by the way, refraction, the bending of the waves. And then on the back of the raindrop, it gets perfect, what they call internal reflection. And when you get that perfect internal reflection, it comes back, reverses the order of those rays, the prism effect, and then comes out and gets bent a little more. That's what you see in the rainbow. And that's why it's only at a certain angle, because everywhere else it doesn't get that perfect reflection. That's that. Only one angle will produce that perfect reflection. Okay? It's called total internal reflection. Everything else is just mucked up and messed up. So that's why you don't see any colors here. Only at that angle. Okay? Now, go a little bit further. Now, the other thing, which is the brighter rainbow? The inner or the outer? The inner, obviously. Most times you can't even see the outer. Okay? Now, another thing to notice. Red is on the outside of this one, but if you can see this, red's on the inside of that. And the violet, the blue, and the yellow is on the outside. Every time, folks, it doesn't vary. Okay? So what's going on there? Well, this next time, now they could have done it up here or down there. They just chose to do it down here. If that sunlight comes in just in a glancing glow here, it gets enough refraction that it does have total internal reflection here, but then it hits the surface again at enough of an angle so it gets total internal reflection again. So it flips the colors once and then flips them again, and they come out in reverse order, just like we notice here. But if you think about it, a lot more sunlight goes through here than goes through there. Okay? Only a little sliver goes through there, so this is always faint. This is always brighter. And sure enough, that model fits what we see in nature. Is it absolutely true? I don't know. But you only have the raindrops in the air after the rain, not before the rain. Right? So yeah, everything seems to fit. The closest I've seen to something like that, my wife's family used to like to go on big vacations about every 2 or 3 summers. And one summer we went to the Tetons in Yellowstone. Boy, folks, if you got a bucket list, put visiting Yellowstone on your bucket list. That is just about the most phenomenal place on the planet. I mean, it's just absolutely incredible. And we were driving from Jackson Hole, or in Jackson Hole, driving toward Yellowstone when we saw it just rained that morning, afternoon, and we were driving, maybe coming back from Yellowstone, I guess we were, and we looked out to our left to the east, and there was this just gorgeous rainbow with that second rainbow. Yeah.
Does it have to be rain that produces a rainbow?
As opposed to?
Seems like I've had my hose from fan spraying with rainbow.
Okay, water. It has to be water. Water. Yes, exactly. Now, the closest I've come to seeing a rainbow.
Faithful.
Huh?
Old Faithful, I've seen a rainbow.
Absolutely. And the thing is, what it needs is water in the air and some sorts of light behind it. I have seen a rainbow light thing with my headlamps on a really misty day. You can sort of see a little rainbow there. You just need water and a source of light. Okay?
It doesn't have to be rain though.
Not rain. It has to be water droplets. Water droplets. Okay? Most common source for something like this would be rainfall. Okay? I thought you meant ice. Ice won't do this. I don't think. Okay? They make what they call snow dogs or snow crosses. That's ice creating that phenomenon. But this is the model of a rainbow. Why it works. Okay? Oh, nice. Where did you take that one? Okay. Were you facing east? Mm-hmm. Yes, I know you had to be. Oh, very light double rain. Wow. And when was that? Recently? About a week ago, yeah. Okay. Fantastic. Perfect example. Okay. All right. That ends chapter 1. And on the way, I neglected, I wasn't turning my pages. There's a little green blurb at the top of page 15 on Science and Society. They have these different blurbs throughout the book. And this is basic as opposed to applied science. Just to give an idea of this, James Clerk Maxwell, that was basic science. Heinrich Hertz, when he was doing experiments, that was applied science. Albert Einstein, basic science, okay? The people who have developed things based on Einstein's work, that's more applied science. This is gross generalization, but most of what my wife has done and what I did in University of Georgia, we were applying principles other people had already developed, okay? So it's a good little article, several questions to think about. If you find they're interesting enough to you that you want to write a paper on it, that would be a good source for the ideas for a paper. You need to go outside the book to get your source for the paper. Okay? Now, he has a little thing, Seekers of Pseudoscience. I don't even bother reading those things, but let's go back here. I wanted to point out when we were talking about Charles's law, temperature and pressure and volume. No, this is actually, temperature and volume. This is what we were talking about. When you plot temperature on this axis, volume on this axis, if you get a nice straight line like that, that tells you two things. Direct relationship. Remember, direct proportionality. Increased pressure, volume, increased temperature, you increase the volume. Okay? And the other thing that it tells you, that's true for most of the range of temperatures. Pretty good illustration of that. Okay? There's a little science sketch. Sometimes those are interesting to read. Oh, in our book, I think it may be even prettier than that. Okay? Let's see if I can get an area there. That's a remarkable rainbow. There's the second one up there. Okay? And the same description. Oh, and here's another one. And a couple of you were in the first class, Physical Science 111, and we talked about plate tectonics. Originally, that was called, what was the name of that? Continental drift. That was what it was called. And the guy who first came up with the theory on continental drift, he said, look at this. South America looks like it would fit right into the armpit of Africa. Look at North America, how it slopes up this way, but Europe slopes the opposite way. They would fit like a glove. The top part of Africa almost fits into the Gulf of Mexico here in the Caribbean. It just looks like a perfect fit there, or close to it anyway. Here they show South America going into Africa. You have to tell Africa a little bit. He looked at this and said, hey, I think the continents are actually drifting apart. Okay? An observation, of course, it's very difficult to measure. He was laughed out of the room. People said, are you nuts? Continents don't move. They're continents. They're there. Okay? They're fixed. Okay, it's sort of interesting they look like that, but they couldn't be. Couldn't happen. He was ridiculed. Maybe kicked out of his society. I don't know what happened, but he was not considered a very bright guy. Until a few generations later, and people started measuring things from the bottom of the ocean. They noticed in the Atlantic there was this ridge, and they noticed all this volcanic activity, and sure enough, now we call it plate tectonics. The plates are drifting apart. Okay? And the Atlantic is getting a little bit wider. Very little, but a little bit wider every few centuries or decades or something like that. Yeah, it is happening. So that means Pacific is actually getting smaller, not by much, and that's why you have the ring of fire around the Pacific. Because wherever the Atlantic is spreading, the Pacific has to contract, and you have plates undercutting other plates, and that's why the San Andreas Fault in California, pretty major. All those earthquakes they have in Japan, think Fukushima, and the others, they've had one more recently. Those in Peru and Chile, that's the ring of fire. That's where volcanoes and earthquakes are crazy. Indonesia just recently had another earthquake, okay? Because they're in that contraction zone where the plates go.
We had the first ring of fire in that
Johnny Cash has heard of it. No, I'm just kidding. That's
It's just,
okay. Yeah.
It's just the,
It-
I'm aware of the eruptions
You what?
I've never heard it called that.
Oh, well, I've heard it called that. Let me get Dimitri Clark to it. Yeah, it basically the Pacific Rim. That's where lots of your volcanic and other activities
I
are.
agree with you.
But some people call it the Ring of Fire. It may not be all that
I learn
common.
something every day.
Okay. Don't bank on it. Okay, no, anyway. So anyway, now that guy who suggested continental drift, even though in his day he was considered ludicrous, now he's considered a really bright guy, you know. But he was dead long before they recognized that he was absolutely right. Okay? All right, now, at the end of every chapter, and by the way, I'm going to say this every chapter, so get used to hearing. Nothing replaces reading the chapter. Okay? I can stand up here and talk about it. You can look at the PowerPoint. You can do all this kind of stuff. But I can't go over everything in the book. And I can't even attempt to. It takes too long. Nothing replaces reading the book. So please read the chapter. Now, after you've read it, then a good idea to do is to look at the summary. The summary tries to hit the high points. You can't hit them all, but it hits them. They usually will put some of the important words in italics, so pay attention to those. And then in every chapter there's at least one focus on some scientist. And I had never heard of this gal until I read this book. Her name was Florence Bascom, a U.S. geologist, expert in the study of rocks and minerals, founded the geology department at Bryn Mawr College, if I pronounce that right, in Pennsylvania. Incredible scientist. And I hate to say it this way, incredible also because she was a female. Back then they didn't even want women going into science, okay? And yet she did. She overcame so many obstacles, okay? So she could be your paper topic, but this can't be the source for your paper topic. This can be the source for your ideas, but it can't be the source. You have to get outside source for your references. Then there's always a list of key terms. Now these are given alphabetically, but they list the page number on which that term was either introduced or defined or described initially. Okay? Now the very best thing to study for most of the tests, this first test may be a little less important on this one, but on most of your tests, which will be mostly multiple choice, there are applying the concepts. This one has 44 multiple choice questions. Okay? That's a little fewer than some chapters will be. Of course, this is a very short chapter. It gives the answers here. That's a great thing to study for most tests. Won't be bad for this one, but you'll have to do a bit more calculations on this test. Questions for thought. Here are 10, which is a few fewer than normal. For further analysis, 7 is a few more than normal. But then, and this will be important on this first test, these Group A exercises. These are the ones like those examples that we stop and do in the middle of the book. This is what a good thing to study here. Okay? And I would say work on most of those. Now, if you have the big book, the answers for Group A are in the back. But if you have the little books, I haven't been able to find them. And I specifically requested that they put the answer to Group A in the back of the book. And I don't think they did. Of course, I didn't buy a copy of it, but I haven't found it. When the students have gone me theirs, I can't see it. So, sorry about that, but if you have any questions, you can ask me. Yeah. So, again, at 5:45, we will cease and desist and go to the lab and do our experiment, this first lab, which will be, as I said, the longest, most involved lab we do all term, okay? And then Tuesday, the last 30 minutes of class from 7:15 to 7:45, you'll have the first test. And it will be more quantitative than any of your other tests. It's not that much, but it'll be more quantitative than most. Okay? No, it's Tuesday. Okay. So what we're going to do now is continue in chapter 2. Okay? In chapter 2, we'll probably get far enough today to come close to covering enough for your first test, but if not, certainly in the first 2 hours of Tuesday, we'll cover enough for your first lab in chapter 2. So, any questions on chapter 1? Lab today, 5:45 to 7:45. If you finish early, you go early. Okay? Tuesday, 2 hours of class, 2 hours of lab, 30 minutes of test. You probably won't take 2 hours to do the lab. If you finish early, you can start the test early. If you finish the test, you can sayonara. You can take off. Okay? So, let's move on. If there are no questions on chapter 1, let's move on to chapter 2. Any questions so far? What is it now? Getting close to 5. So at 5:45, we stop and do the lab. I think I have most of it set up. I have it run off, so hopefully we won't have much delay in doing it. Now, it looks like a few people are taking a little break now. Not a bad idea, a good place to do so. So I'll get this set up, but we'll pause here. All right, we're getting our projection back. Again, I ask any questions on anything so far? All right. Well, chapter 1 was basically one of these sort of nebulous, covering everything chapters. What is science? Now we get into what I consider the real physics. Okay? Chapter 2 is going to talk about motion. How would you describe or define motion? Movement, okay? That's almost from the same root. You were one place, you wound up someplace else. You had to move to get there. That's what motion is. Now, 2 things are involved with that. Going from here to there, what 2 things are involved? Say again? Okay, now that's coming in a later chapter, but yeah, you're absolutely right. But I'm going to talk about the motion itself. Distance. Someone said it, didn't they? Okay? You move the distance. And the other thing, even on Star Trek, when it was beam me up, Scotty, it still took time to do so. So those are 2 features we're going to talk about in this chapter. If you remember back in chapter 1 that we did on Tuesday, we looked at some of the things. It was mass, length, time, temperature, some of those were the basic features. We're going to focus on the distance and time in this chapter. Okay? That defines motion. Now, what you were saying with energy or work, stepping back a notch, a net force is required for any change of your state of motion. So you're absolutely right. It took some sort of effort to get from one place to the other place. So a net force is required. Now, we haven't defined what a net force is, okay? That's not one of the 4 basic, 5 or 7 basic things that we are studying. It's a combination of those. So that's required for any change in the state of motion, okay? So, what is motion? Well, in order to answer that question, we'll first describe the motion. Then we will explain the motion. That's where the net force comes in. Then we'll give a few applications of that motion. So that's how the chapter is split up. Basically, we'll first start with describing the motion, and that will be our second lab. Okay? Then we will do explaining the motion, and that will kind of be our third. I'm trying to think if it's also the 4th lab. I believe so. And the applications will be applied to that, and that's mostly the 4th lab, the 3rd lab in this chapter. Okay, so how do we describe motion? 3 basic concepts here. Position, then speed and velocity, and then acceleration. Y'all deal with all of those, right? You're changing your position. In order to do so, you had to have some speed or velocity to do so. And what is speed or velocity? What is speed or velocity? Change in displacement per unit time. Miles per hour, feet per second, meters per second, or meters per hour, or something like that. Kilometers per hour. That's what a speed and a velocity. So are speed and velocity the same things?
Yes.
Close, but not quite. Okay? We'll talk about that a little bit later. Now, so speed or velocity is the change of position per change of time. What is acceleration? Any ideas?
How fast?
Say again?
How fast you move, progressing, like how you moving, constantly moving.
Okay? And I think what she's getting at there, that's the rate at which you're changing speed. Right? The speed is the rate at which you're changing your position. Acceleration is the rate at which you're changing speed. Right? You're not accelerating if you're going at a constant speed, right? Okay? You are accelerating if you're changing that speed. Okay? Or changing more precisely the velocity. We'll talk about those differences in a little bit. Okay? Now, we'll have three applications of these. The first application will be horizontal motion. It says on land. And it says horizontal motion. Actually, we're going to do motion in one dimension. It won't be horizontal, but it'll be only in one dimension. Okay? Then we'll do falling objects, which again is one dimension, but now it's definitely vertical. Okay? And then the third is compound motion. That's in two dimensions. Okay? Movement this way and that way, horizontal and vertical. That will be the second lab in this. The first lab in this chapter will be straight line motion. Not quite horizontal, but close. The second one would be compound motion when you're moving in two dimensions, not in just straight line motion. Okay? That would be the third lab, second lab in this chapter. Okay? Then the next big section here will be how you explain motion. And the basic ideas behind explaining motion are forces. Okay? And we'll give a definition for forces, we'll do applications of forces, we'll do that. That will then lead to another concept, one called inertia. The third lab is going to investigate that. Forces, inertia, mass. And these are all wrapped up in Newton's laws of motion. And we'll mention again, remember we mentioned Newton before? Follow Galileo. Newton's first law of motion came almost directly, basically directly from Galileo's work. Galileo came up with it first, yet somebody there, it was given the name the law of inertia. But then Newton expanded on that one and came up with two more to give the three laws of motion. Okay? Now, we'll do applications with these. These applications involve the concept of momentum and impulse, and those are very, very, very closely related. We'll do an application of circular motion. Okay? And we'll do another application. Guess whose name's on this one? Newton again, his law of gravitation. And we'll look at some applications of that with Earth satellites. Okay? Now, if it seems like Newton's name shows up a lot, it does. Okay? For instance, he came up with the three laws of motion. Like I said, Galileo had come up with the first one pretty much, but he expanded on that and came up with two more. Okay? Newton also did the law of gravitation. No one had explained or described gravity in any meaningful sense until Newton did. Okay? Remember when we were talking about the rainbow splitting light into colors? Newton came up with that concept too. He was the first to come up with the theory of light, okay, and what makes up light. There Newton was again. And in order to do all these other things, the math of his day just wasn't adequate. developed a new math called calculus. Calculus is the math of instantaneous change. And we'll be talking about that in this chapter as well. We won't talk about calculus, but you see Newton's all over that as well. And Newton came up with ways to do lots of things using calculus that nobody has gotten any better on. Now, people have advanced, like Einstein came up with some ideas on gravity that went beyond Newton. Newton couldn't possibly have come up with those in his day because it just wasn't enough known then. But I tell you, haven't been many minds any greater than Isaac Newton's. All right, so let's get back to motion, okay? Now, before we measure motion, let's sort of describe it. Two fundamental components of motion. We've already talked about them. What are they? Anyone remember? Components of motion. Distance and time, okay? The two ones, a change of position, okay? Change of position. That has to happen for motion to occur. You're not moving if you're standing still, okay? To move, you have to change your position. So that's one. And with a change of position, you have a change in time. Now, I'm going to introduce a sort of a nomenclature here that the book doesn't really do, but to me, it just makes more sense to use this kind of a concept, okay? And that's this one. Let me get my pen set up. When you talk about a change of position, what do you want to name the position? Pick a letter or something to represent a position. A? Okay. So if you're started off at one position, A1, and move to a different position, A2, that change is a delta A change in A change in your position. Now this delta, that means a difference in it. That's why they use delta, difference. You were here, you wound up there, that was a change of position. That's usually measured in length, right? Okay? Change of time. Time is almost universally little t. So that would be a delta t. Change in temperature. Difference in temperature. I mean, not temperature, time. Difference in time. Okay? So, that's what we're talking about. Change of position, change of time. Now, how are these related, or what do they relate to? You want to know what distance over time is? Think of it. Second? Okay. What is difference over time? Change of different distance over change of time. Distance over time. Speed, exactly. Or velocity. Okay, we'll talk about the difference in those now. Here's an illustration of that. This is pretty simple. Let's say that you're in a car, zooming along here, and let's say you start at position 0. Okay, 1 minute later, you pass a mile marker. Okay, another minute later, you pass another mile marker. Another minute later, you pass another mile marker. Another minute later, you pass another mile marker. What would you say about your change of position? Constant. It's constant. You're going at exactly 1 mile per minute. What would that be in ways we usually think of it? 60 miles an hour, of course, because there's 60 minutes in an hour. If you're doing 1 mile a minute, you're going 60 miles in an hour. Now, 60 miles is 60 minutes, which would be an hour. So you know the speed right from that. Okay? Most of you probably don't ever go that slow. Oh, of course you do. Okay. All right. Now, and that is also, as you've already pointed out, constant speed. Constant speed. No change in your speed. Okay? Now, there are 3 important combinations of those lengths and time. This is what I was getting at before. And the first of these, and you've already said it, is speed. Okay? Now, what is speed? Yeah, it's the how far you've gone and how much time. Okay? That's it. How far you traveled in so much time. Now, if I drive from here to Tuscaloosa, more than likely, I'm going to get on the interstate and go just about, might even put on cruise control and go to constant speed, and that would be how far I travel in a given time. Maybe 70 miles an hour. If it's crowded or something, it might drop to 65, something like that. That's speed. Now, the second of these is velocity. And isn't that the same thing? Not quite. Velocity, okay, let's back up a minute here. Change of position can be described as a distance, right? Distance is merely a scalar quantity. What does that mean? It has a magnitude. How far did you move? Okay? So many feet, so many miles, so many furlongs, whatever it was. Change of position. There's another concept that's very similar to distance, and that's displacement. I was here, I wound up here. Now, if all I'm interested in is distance, I just measure the distance. But if I'm interested in, I went so far south and so far west, or something like that, now you introduce the concept of direction. Distance is only a scalar quantity, so many feet, so many miles. Displacement would be so much distance in a given direction. When you include direction into your concept, you're now talking about a concept we call a vector. A vector is a measurement, has a number to it, but it also has a direction associated with it. For instance, I'm just going to round it off, about 20 miles to work this morning. Okay? I'll drive about 20 miles home. Okay? Makes sense, right? Going the same, from the same two locations. Okay? However, I drove 20 miles southwest from home, and I'll drive 20 miles northeast to go back. So my displacement is different because they're in different directions. The distance is the same, but the displacement is different. A vector includes a direction. A scalar just includes. So, here's the concept here. Scalar, just a number, that's what speed is. How fast are you going? Velocity, how fast are you going in what direction? Velocity is a vector quantity. So get this. Speed, scalar, vector, velocity, vector. They even start with the same letters, okay? Not everything does that, but these do, okay? So that's the difference in speed and velocity. Velocity involves a direction. Now, sometimes we'll use the little symbol V for velocity, but if we don't, if the book doesn't bold it, or you don't put an arrow over it, you usually let that represent the same thing as speed. Now, this book is notorious for treating them almost like they're the same. But in reality, in real physics, velocity is a vector quantity, speed is a scalar quantity. Okay? The third one of these is acceleration. Now, what was speed or velocity? Speed, change of position per unit time. Now, I call that by a different name too. And this is, I don't know, I guess I've been in so many math classes, okay? It's the time rate of change of position. Time rate of change. How is it changing over time? Okay? Whereas velocity is your time rate of change of your displacement, which means a vector, a direction is associated with it. Okay? What is acceleration then? The time rate of change of your velocity. Because acceleration just about always has a direction associated with it. Now, we talk about acceleration without involving direction, but just about always it really does involve a direction as well. So it's the time rate of change of velocity. How is your velocity changing for a period of time? Now, I bet you some of you relate to this. I know when I was growing up, a lot of the guys really put a lot of emphasis on their vehicles, and they said it can do 0 to 60 in
20 minutes.
okay, that's my vehicle. Okay, they were talking about 4.3 seconds, 3.9 seconds. What are you talking about then? What's 0 to 60 stand for? 0 to 60, though, is talking about miles per hour. That's a change of velocity. And what's the 4.3 seconds? 3.9 seconds, or whatever? That's your time period. So you're talking about acceleration. How fast can you, how great is your acceleration? Okay? And that's usually directly related to your horsepower. You know, and so that's what they were bragging on. Okay? Time rate of change of velocity, that's acceleration. Okay? Now, of course, in that one, you got miles per hour as your change of velocity per second. So you've got your time units, 2 different time units there, but that's still an acceleration. Okay. Now, all right. What is speed? We've already said that, talked about it some. It's a change in position, okay? Change of position, change of distance with respect to time. Delta P, delta A, whatever you want to call it, over delta T, change of time. Now, there's 2 types of speed. One is an average speed, okay? Last weekend, my wife and I went over to Atlanta. It was my 45th anniversary of my graduation from college, okay? I went to Georgia Tech, and it was our 45th reunion. It was homecoming over there. We lost. But the deal was, I was in Navy ROTC, as I mentioned. Our unit, had about 3 years ago, everybody started getting in touch with one another. I hadn't seen any of the guys or hardly thought about them since I graduated from Tech. Everybody went their separate ways. But some of them got to thinking it'd be nice to get together again. So 2 years ago in December, we went down to New Orleans and had a little mini reunion there. And we decided to do it again at homecoming at Georgia Tech this year. So we went. Now, our average speed would be how far we traveled. That's about 150 miles, right? From Birmingham to Atlanta, approximately. 150 miles. And it may have taken us 2.5 hours. Okay? Now, if you broke that down to miles per hour, you could do it. It's not hard to do. Does that mean we were traveling that speed the whole time? No. When we were on the city streets, we were stop and go, fast, slow, never very fast. Stop through fast, we were going slow. When we got on the interstate, we were zooming. My wife was driving, so we were zooming, okay? But we did stop and get gas, and I think we stopped to eat, okay? So those stops were in there. Those were the average speed. Sometimes we weren't going anywhere. Other times we were going along pretty fast, okay? That's average speed combines all that. It's the most common measurement. How far you went, how much time did it take, okay? There's another speed, though, and that's the instantaneous speed, okay? That's when the time interval, that delta T you divide by, change of time, when that is reduced and you go down to 0, okay? Now, I can't remember. Zachary is kind of here now, okay? I had marked you by mistake and circled, but now you are here, okay? All right, pretty good attendance today so far. We're still missing Tyler Scott Latham. Does anyone know who he is? Was he in any of your programs? Not a familiar name, so don't know who he is. And the other two, I know Sarah Warren. She's on the school's volleyball team, and quite often they're in volleyball matches, so I'm guessing that's where she is. I don't know Clinton Lamont Wilson Jr. Does anyone know him? Is he in any of your programs? No? Okay. So we may not wind up with this many people after all. I think Sarah will be here, but we'll see. Okay. All right. So instantaneous speed is how far you travel as the time interval gets smaller and smaller and smaller, approaching zero. Okay? Now, I don't know if any of you do this. I can remember doing it as a kid just to have something to do when we're on long trips, is look at the mile markers and measure how much time it took us to get from one mile marker to another. That was measuring average speed. We traveled that 1 mile in so many minutes. Okay? Now, what device would you use to measure instantaneous speed, or at least close to it? Your speedometer, exactly. That gives you, it changes, not every instant, but it changes pretty smoothly there, okay? It gives you a pretty good idea of instantaneous speed. When the time interval that you're talking about is basically zero, approaching zero anyway. You can't divide by zero, so that's why we say approaching zero. Now, here is the standard definition. Speed is distance divided by time, okay? Now remember when we did our density equation in the last chapter? That was density is equal mass divided by volume. And did I show you the triangles and the circles? Yeah. You can do the same thing with this. Distance goes on top, speed and time in the bottom, and cover one, and that's how you get the other two. Okay? Speed is distance divided by time. All right. Now that's always instantaneous. Average speed. How far you traveled in what time interval. The time interval is not approaching zero then. Average speed. Now, and again, I get to talking. I forget to turn pages, so let's make sure I haven't left out anything. All right. Let's go back here. And I want to give you the equation that says the same thing as this. Because we don't have a separate variable that we use to represent speed, we often use V, but we use it, the book uses it, italicized. I can't write italics. For velocity, they really should put it bold, okay? So if it's not bold, then it's speed. But this is average speed, and the bar over it means average. That's just sort of the nomenclature of that. And this would be distance over time. Again, you can represent distance in many different ways. This variable, rather than A, they chose to use B, distance divided by time. And that's speed. Even though that looks like velocity, that really is speed. And that's average speed. The bar means average speed. Okay? And that equation is there in your book. Okay? And sometimes you'll call that V bar, by the way. Now, all right. Let's do this first. It's not really an example per se in the book. They don't label it as that. We'll come back and do an example in a little bit, but let's do this figure here. It says here, calculate the average speed between the trip times of 1 hour and 3 hours. Okay, at 1 hour we're at the 50 kilometer marker, and at 3 hours we're at the 150 kilometer marker. So what's your average speed between those trip times? How would you do that? So average speed is, what do you say? Anybody?
D over T.
Again?
D over T.
Okay, D over T. Now, I like to use that delta notation. So I'm going to show you the delta notation. Change in displacement or distance over change in time. I like to use the delta because it describes what's going on better to me. So what's your change of distance? Okay? Now here's what the delta represents. Always, no matter what follows the delta, it's final minus initial. Always difference, that's subtraction, right? Always final minus initial. So what's your final distance? So we'll do df minus di over tf minus ti. That's what delta means. Final minus initial of whatever you're measuring there. And what was your final distance here? 150 kilometers. Keep the units. Don't just give me a number. Minus. What was your initial displacement? 50 kilometers.
What page is
Second. This is top of page 27, right-hand column. Yeah. You see the figure? Okay. So there's your numerator. What's your denominator? What was your final time? 3 hours minus 1 hour. Okay? So what's your change of distance? 100 kilometers. And what's your change of time? 2 hours. So what was your average speed? 50 kilometers per hour. Keep your units. They're your friends. They help you know whether you're measuring things right. And speed is typically measured in miles per hour, kilometers per hour, feet per second, whatever. Okay? Distance over time. Make sense? So your elapsed time was your 2 hours. Your total distance traveled between those 2 hours was 100 kilometers. 50 kilometers per hour. Not moving all that fast, folks. That's approximately 30 miles an hour. So that may be in-city driving or something like that. Okay? Make sense? Okay. Oh, let's see. They're going to answer their own question. I forgot they were going to do that. So let me erase my scratch. So velocity is distance over time. What is your distance? Oh, they don't tell us. Well, look at that. Well, we did it. That's what I did. Change of displacement. That's 150 minus 50 over change of time. 3 hours minus 2 hours, 1 hour. That's 2 hours. So 100 divided by 2, 50 kilometers per hour. Okay. Now, before we move on to velocity, okay, I think I'll use this space here. All right. Now, the slideshow doesn't show these. I think they're very helpful. So the book does emphasize them, but the slides don't. So I was just going to point this out to you. Here is a graph of distance over time. Okay? Y'all familiar with graphing? Usually, not always, usually we put the independent variable, horizontal axis, the dependent variable, the vertical axis. Which you think depends on which? Does distance depend on time, or does time depend on distance? Usually time is independent, and your distance depends on the time. So that's how we put it. So if you travel 1 or 50 kilometers in 1 hour, another 50 in the second hour, another 50 in the third hour, that's a graph of what we were just looking at. Now, what do we call, what's the characteristic of that line? Just the line there.
He's gonna have my schedule mixed up.
Okay. And what's your name, please?
Talent.
Okay. Oh. Okay.
Yeah, I thought it was the same time as my class I had yesterday. I thought it would start at 5:30, and I was like, whoops.
Oh, no, that's the lab. Okay. So you go by Tyler?
Yes.
Okay. All right. And let's see. You just made it in class time, so you get counted as here today. Okay. Now let me have a little time out here just to catch Tyler up. Yeah, that's all right, but you need to know this. Okay? I teach, and I forgot to tell y'all this, but mentioned the things, but I didn't do it. I teach using a package called Screencast-O-Matic. It's not a very good package. It's cheap, and that's why the school uses it. And what I do, it records everything that's projected on the board with everything that I say. My microphone's in my computer here, so I try to stay close to this. It records it in sync, okay? And then at the end of the class, I upload it to YouTube. And then when it finally uploads to YouTube, which usually takes a few hours, then I'll move it over to a playlist, okay? Now, to access that playlist, you go to the Blackboard. Are you familiar with Blackboard? Go to Blackboard, and in Blackboard, you know, there's a whole bunch of columns. You get in this class a whole bunch of tabs over here, bright blue color, okay? Sort of like that blue there. It's more like this blue, okay? And now, I don't have it set up yet, but when I get it set up, one of the early ones will say, what's the first one? It'll be something about the syllabus. So it's not in there yet. I've got to do a few corrections to it, and that will be there. Not there yet. It's empty right now, but it will be. Okay? Then another tab or two down is something about the instructor information. And that's where I'll put my locator card that shows when I'm on campus, off campus, which campus I'm on, in class, out of class, office hours, that kind of stuff. What kind of stuff. I don't have it there yet, but I will have it. Then you go down several more tabs. I don't think you have to scroll anywhere, but several more tabs. Then you'll come to one that says class handouts and more. Okay? On that one, not only one thing's there now, but in time, the research paper instructions will be there. All of the PowerPoints for all the chapters we're going to do will be there. And my YouTube videos will be there. And right now, I have the link for the YouTube video. That's the only thing I put on Blackboard so far, but I put it there so that people who missed Tuesday will be able to go back and listen and see what we talked about on Tuesday. Okay? We talked about the syllabus, so you can find out about the syllabus there. We talked about the research paper. You can find out about that there. I talked about my locator card. You can see the last version. It's not the current version, but I explained what was the changes in it. And then you can look at the PowerPoints that we've had so far. We finished chapter 1 earlier today. In 10 minutes, we will be starting the lab for chapter 1. And next time, we're in chapter 2 right now. Next time we'll do the first 2 hours in chapter 2, and then we'll have 2 more hours of lab for the first lab in chapter 2, and then the last 30 minutes will be your test from chapter 1. And the reason I do it that way is everybody be here for the class part, and then the lab part. If you finish the lab part early, you can start the test early. If you finish the test early, you can go home. If I did it the other way, you'd have to. If I did the test first, then everybody would have to sit around until the last person finished the test. Then we would start class or something like that. So I figure it's better to have the variable thing at the end so you can leave early. Okay. So you can go back and see everything we talked about. Yes.
You said to open those tests.
Second. Oh, okay, right. Thank you. On every test in this course, okay, sorry that, I think of his name now. Gary, I think it is, isn't here, but I'll try to remember to tell him. Every test in this course, including the final exam, you can bring in with you a formula and equation sheet. And on that, you can write anything you want to. Anything you want to. Definitions, yeah.
So we basically just bring it. So we use a formula and equation sheet?
Yes, you can use your formula and equation sheet during the test. So you can bring in anything you want to on a piece of paper, front and back, written as small or as large as you want to do it, organized however you want to organize it, and bring it with you for every test, including the final exam. So I highly recommend you do that, okay? That way you don't have to memorize things. Because guess what? If you were working for me and I had a problem I wanted you to solve, come up with a program, a plan, or something, I don't want you to say, oh, I think this is this. You know, I want you to look it up say, this is what we're using, okay? I don't want you going by memory. I want you to look it up. So write down anything you might need to look up for the test, okay?
So our notes.
yeah.
We use our notes.
Yeah, but condense on to one piece of paper.
One piece.
Yeah. Now, here's a reason I do this. When I was an undergraduate, very seldom did any professor allow us to do that. But especially when I got into upper level courses, occasionally one would. Boy, I jumped on that opportunity. That night before the test, I would sit down, I'd go through the things, try to organize and get what's the important stuff, what's not, get it in a way that I could read it and find it real quickly, put it together and, did. And then when I went to take the test the next day, sometimes I'd forget to look at it because that was the best study tool I could imagine, is to write a formula and equation sheet. Because if you organize it, you plan it, you prioritize it, you do all this stuff, and then I'd forget to look at it. Oh, I said, oh yeah, that's right, I got it right, But I would suggest for every test you ever take, do a formula and equation sheet. Now, if your instructor doesn't allow you to use it, don't use it, okay? But that practice of writing it down, summarizing, putting it down in concise form, best study technique I know going. Gary, I was just telling him, for every test, one Tuesday and every one we do, including the final, you can have a formula and equation sheet. Anything you want to write down on a piece of paper, you can bring with you for that test. Okay, fantastic. Okay, so I came back here so that I could okay. They do another couple of things here. In fact, I think I'll go back to the other. Okay. This one, okay? Okay. Remember I said this is average speed is equal to distance over time. That's the way the book does it. I put deltas in there, but you don't have to have the deltas. What if you're interested in finding the distance, but not the speed? Yes, multiply both sides by the time, and then you get distance is equal to velocity or speed times time. And that makes sense, doesn't it? So many miles per hour times so many hours will give you how many miles you went. Yes?
I know you mentioned it before, but the bar with the V, what's that for?
That stands for average.
Oh,
That's average speed. Okay? Okay. Sometimes I'll almost put an arrow on it. I don't mean to. That would be a velocity, but that's not what we're talking about here. Okay? What if you were looking for time? How would you get it? Divide everything by the average speed. Okay? And then these go out. T is equal to D over average speed. So that would be how long it's going to take you to take your trip. Okay? Now, and as I told you before last time, you can use the little triangle or circle. Okay? Whatever's on top goes on top. And the other two go beneath, speed and time. Okay, let me put average velocity, average speed. Use the same V they did there before. Okay? V bar. Okay? So if you're looking for average speed, it's distance over time, just like this. If you're looking for time, that's distance over velocity. That's from here. If you're looking for distance, that's speed times time. That was this one right here. Distance equals speed. So you can do it that way and not even have to worry with it. But all those work. Okay. Now, let me clear my scratch. It's okay too? I'll leave it up there for a little bit longer. Okay. All right. Now, I don't know. Okay. The question is, do we have time to do example 2.1? I'm kind of guessing not. So let's plan to do that first thing on Tuesday, okay? We'll start with example 2.1 on page 28, okay? Now again, as I said for chapter 1, let me emphasize it here too. Nothing replaces reading the chapter. So as you're studying for chapter 1, definitely read the chapter for it. But if you have spare time in there after you've read chapter 1, read at least as far as we've done now, plus as far as you can get in chapter 2. Because if you've read it before I talk about it, even though you're maybe not understanding it all, hey, guess what? When I start talking about it, you'll have some framework to put it in. If you haven't read it, then my blah, blah, blah up here may be as confusing as it would be reading the book without any explanation before. Everything that you do adds to your understanding. So I suggest read it before we come to class. All right. Let's pause the recording. Now, does everybody have, you don't have to do those calculations yet, many of you, I bet you have. You've got the surface area, the small cube, the medium cube, the large cube, the volume of the small cube, medium cube, and large cube. Everybody got those done? All right. You can wait and do the calculations later. We'll do those together if you want to, but if you already started them, that's fine. All right. The next thing we're going to do is, not yet, but close. Okay? We're going to have some boxes. Little boxes made out of ticky-tacky and all lined in a row. Okay? All right. Now, with your clear, with your clear, let me hold this quickly. With your clear rulers that you can see through, the first thing you're going to do here is measure. Now, by the way, okay, let's have, you need the left, sir? All right, if you need it, we can move out somewhere else. I'm sorry?
We will be more like big block. If you're not done, that's fine.
Okay. Now, you have 3 teams. Each team has a box. Now, you decide. You want number 1 to be the small box? Okay. You have the small box, so your measurements go in column number 1. This is on page 24. You have the big box. Okay. So your measurements are going to go in number 3. You have, where is it? The medium box. Your measurements are going to go in the middle column, number 2. Okay? Now, listen up though, before you start making your measurements, listen up. Notice it says the length, the width, and the height. Now, one problem with these boxes, they're not rectangular parallelepipeds. Okay? They have a slant on this side. So what you do here, and again use the centimeter side, and notice it doesn't start at the end of the ruler, but go to the middle. You see the slant, get in the middle of the slant, and go to this edge, and do your best guess of what that length is. Do your best guess of what the width is, and do your best guess of what the height is. Okay? See what I'm talking about? You have to do your best guess taking the middle part here. Because it's the middle part of the slant. Okay? Now put it in the right place, share it with your teammates. Okay? And record those measurements.
Isaac, get some measurements. Yeah, 95.
25. Number 3. The length, width, and height.
16 and a half. Eight and a half.
Be sure this table put yours on column 3. You put line, they put theirs on too.
3.5 on high.
Hot. Nobody needs the meter sticks anymore, right? Probably, yeah. Because you're gonna have to open the
Water.
Okay. Why are you not getting any water? Okay. No, okay. All right. What you're doing, whether you realize it or not, is following mass and volume part C. Okay? And you've done the first part. You've done now you're ready to do the second part. It's on page 17. Unfortunately, I only have 2 working scales. Before you measure any mass, zero the scale. They're not zeroed initially necessarily. Be sure you zero the scale and then place the empty container with no drops of water in it, okay? The empty container on the scale and measure the mass of the container. Y'all have. No, not yet. Better to do it this way. Put it on the scale, and you may need to wait until they finish and pour the water very slowly into it. Okay.
Can we use your scale? Are y'all there? Can we take it to the Oh, wait. Y'all need it?
Now, these are your blocks. What's that? This is 3 blocks. Wait, no, you had. I had 3 boxes over here, didn't I? Just 2, I'm sorry. I think originally I did. You had to have enough control. Only 10 of this and 10 of that. And you got 9, 18, 20, 24. Did y'all get blocks from another thing? Wait, take the scales through. Put do want to try those, man.
Oh, sorry about I was meeting.
Why is he leaving full?
Oh, okay. Huh? Where is your container? Oh, there it is. That's not that. Zero the scale before you from the back. Zero the scale. Done it already? Okay, zero the scale. Zero the scale. Then put that on and determine the mass of the box. That's what you put.
Almost.
I got all this. Put enough water in there. Put enough water in there to fill that. Fill it in here. Yeah.
Oh yeah, like if I it's like that water or back into the
I'm really secure about it.
or back into here.
Well,
I see skinny as a speedy or brought back over. I wouldn't hear it. I would say I was skinny.
I was measuring over there, and they filled up the container.
Okay. Let me have a timeout, folks. It sounds like people are getting way ahead. And here's what you need to do. Okay, if you're following the directions, you will see it. Okay, now unfortunately, these two teams are sharing the scale, so that just can't be helped. Okay, but say it. Okay. So what you do, if you haven't done this, you have to redo it, but it won't take long because you know how to do it. You put the empty, you zero your scales first. Zero the scales first. I hope you zeroed the scales. Okay. Then you determine the mass of the container when the container is empty on the scales. Okay. Then you pour water into it until it's absolutely full. Okay. Measure the mass of the water and container. Okay. You can go back and do your subtraction later if you want. At that point, you empty your container you poured from. Okay? Fill that up completely. You empty the container you poured from, and then dump the water in there that you know the mass of back into the empty container. Okay? To the empty container. It's not, okay, is that the water that wasn't there? Yeah. Okay, but you didn't have any other water in it. Okay. Now what you do is pour that water into your graduated cylinder. Okay? Don't overfill. This is as far as you can go here or that there. You got more water than it will take to do that. Got it?
No. I always eat it just
For that into here and measure the volume there.
See, this is my head.
It's like important Dixie does. Important Dixie does, yes.
I got my question. You said divided by one.
You have to do the work. We're going to share data. Now, has every team finished their measurement? You may not have finished your calculation. Have you finished your measurement? Yay or nay? Who has the small? Okay. All right. For your other two teams, listen up. Okay. Under column number 1, length of container, 8.3 centimeters. You got it? Okay. Width of container, under number 1, 4.3 centimeters. Height of container, 3.1 centimeters. Skip down to number 5. Mass of container, 3 grams. Are you listening? Mass of container and water, 113 grams. Measured volume of water, 111 milliliters. Okay? Who had medium?
Wait, you skipped the.
Say again? Oh. 8.6 or 8.9 or 8.3, what is it? High. 8.6. Correction. The number 1 length of column of container, 8.6 centimeters, not 8.3. I picked up the wrong paper. Okay. All right. And medium. Okay, the rest of them you can calculate. These are the measured values. Are yours correct? Okay. Okay, number 2. Yeah, sure. Yeah, you got it. Y'all, okay, teams 1 and 3, listen up. Number 2. Length of container, 14.5 centimeters. Number 1 for number 2 is 14.5 centimeters. Under number 2, width of container, 3.5 centimeters. Height of container, 3 centimeters. Number 5, the mass of container, 10 grams. The mass of container and water. I don't believe it. Yeah, it can't be 87 grams. Maybe 187 grams. Yeah. Okay. Well, I don't know. 180 is down here. Okay. I'm going to say the mass of container and water is 187 grams. Okay. And then measured volume of water, 180 milliliters. You go back and redo the calculation. That's got to be a 187. Okay? Who had the large?
You should probably read here.
Who? Oh, okay. Oh boy, that's okay. All right. For number 3, column number 3, y'all ready to jot it down? Okay. Length of container number 1 for number 3 is 16.5 centimeters. Width of container 8.5 centimeters. Height of container 3.5 centimeters. Mass of container number 5, 32 grams. Mass of container in water number 6, 430 grams. Number 8, measured volume of water, 413 milliliters. Okay? The rest of them are calculations. Okay? Do y'all feel comfortable doing your calculations on your own, or do you need some guidance? We need all our guidance. Yeah. You don't have to.
Oh, this one is not.
You don't have to. I'm only going to grade what you. That's why I gave you scratch. Okay.
What's the calculated to measure?
Hey, cut, don't you think that?
Yeah.
No, I didn't feel like going in there. I was like, yeah, but it's coming in. And jump back. Well, like this. So you don't know if he's better. It's okay. I sort of know if you had a Samsung cable. You want Samsung? Yeah.
Now, okay. Folks, listen up. Anytime you have these labs that came out of the lab manual, not the ones I wrote, when you see a big space of white space there, that means there's a question to be answered. Okay? Now, you can wait to answer the one on page 16 until you've done the experiment, but be sure you go back and answer that. Number 6 on page 16 needs an answer. Okay? Now, all right. You don't have to answer it right now. Okay. You were working on the third part C, right? And you've done all the calculations on part C? Okay.
Part C, is this C?
C is the part that says mass and volume on page 16, 17, and the top of 18. Okay? Yeah, you were doing that. That's what you were doing.
Oh, okay, yeah.
Okay, on the top right here. Top here. Everybody go to the top of 18 if you've answered all the things on the C part. In other words, on page 24, that's completely filled out. Right? Yay or nay? Okay. Then on the top of page 18, it says, make a graph. Okay? Make a graph of the mass in grams. That's your row 7 data from page 24, wasn't it? And the volume in milliliters, that's the row 8 data, to picture the mass per unit volume ratio found in step 5. That was on the previous page. Put the volume on the horizontal axis and put the mass on the vertical axis. So you see your piece of graph paper is the last page. So you decide how you want to set it up. You can set it up landscape or you can set it up portrait. I don't care. But however you choose to set up, then the horizontal is going to be the volume, vertical is going to be the mass. If you set it up this way, horizontal is the volume, vertical is the mass. You decide how you want to do it. It's up to you. Not going to make much difference. Okay? Now, someone give me the range of volumes that you have there, from the big to the small. And the volume is what? Number 8 data. What's the smallest? 111. What's the largest? 413. Okay. Now let's look at the masses. Let's see. 110 to, okay. So I would do the volume landscape. Do it like this. Okay? And you said 413 was the max, right? So if you do 0 here, if you do 10, 20, 30, 40, 50, 60, 70, 80, 90, okay? I think you could do you do 10, 20, 30, 100, 200, 300, 400. Yeah, you can get it on that way. Okay? So in other words, starting here, 0, 2 of those blocks. So that would be 50, 100, 150, 250, 200, 250, 300. You can get them all on there. Now let's see if that will work for vertical. It may not. So hold on before you do that. 1, 2, 3, 4, 5. Nah. Let's go back and do 10. 10. Yeah. No. Yeah, you can do it. I think it'll work. 0, 100, 200, 300, 350. That'll. No, sorry about that. Okay, go back. 100, 200, 300, 400. 100, 200, 300, 400. It's going to be not a good use of your scale, but it'll work. So do each of those blocks here, 100, 200, 300, 400. 100, 200, 300, 400. Okay, sorry. 100, 200, 300, 400. 100, 200, 300, 400. I think that'll work best. I thought maybe we could squeeze it in. Okay. Yeah, that's how I started saying, but you don't quit. Okay. You got to make it the same. So you have 100 here and 50 there. So close to that. Yeah, do 100, 200, 300, 400. Yes. What's that? Yeah. Okay. So volume. Don't get that. 100, 200, 300, 400.
Yeah, that way I'm not stretching super far between them.
Volume, mass. Okay. Now, so you have 3 sets of measurements, right? Small container, large container, medium container. Okay? So you take those data and whatever the volume of the small container was, find it down here. Mass of the small container, or the water from the small container here, come to a point there. Do the same for medium, and do the same for the large. Okay? And that gives you 3 data points. Right? Okay. Find the volume. Okay, the volume at the bottom, 0 cubic centimeters, 100 cubic centimeters, 200 cubic centimeters, 300 cubic centimeters, 400 cubic centimeters. 100 grams, 200 grams, 300 grams, 400 grams. Right? So let's say your small container was 100 by 110. It's not. I'm just making it up. So come over 100, come up 110, meet right there. That's going to be your data. Okay? And do it for medium. Do it for volume.
I probably don't.
me go back to number 6 and see what it says. I'm super confused. It said row 7. Number 6.
Yeah, basically. I'm 7 over here. It's cool. I feel like halfway through it because it's so basic.
Okay. All right.
Yeah.
So y'all are doing the graph, right?
Yes.
Okay. Once you got the graph done, then get your clear rulers and draw the best straight line you can through those 3 data points. Okay? Not a curvy, wavy, the best straight line. Not bad. Okay. You could have used that on your 4th point, okay. But anyway, what you need to do is measure. Yeah. Rise with the say the difference between these two is rise, and that's in those two.
Okay.
I know that one. Yeah, you're right.
I think in the morning I think yeah, I got 8 o'clock. I mean, it started at 8:30, but he put it back.
Okay. That sounds like a very good question. Now, does everybody have a slope to that line? These facsimiles to it. Okay. If anyone's having trouble with the graph, let me know. Let me check it out. I've seen some troubled graphs. Okay. Okay. Everybody okay? Now there was a question earlier.
Is that what you got?
What is, yes, is that a question? Mighty nice. Now you need to calculate the slope of that. How to do that? Right. You can do these two if you want to. Then right through the origin. So you have to come over here. That makes it not bigger box that way. No, I'm just kidding. Okay, that was a joke.
So redraw the line?
All right. Now, there was a question earlier. All right. Does everybody have an answer for number 8, the slope of your line? Okay. Then it says calculate number 9, calculate your experimental error. What is that slope telling you? What does the slope tell you? It tells you took your vertical line, the rise, and divided by the horizontal. What does the vertical line measure? What's the vertical line measure? Grams. What does the horizontal line measure? Milliliters. And what's a gram per milliliter? That's a ratio, but it's grams per milliliter or grams per cubic centimeter. What's that a measure of? Density. So that is your density. You just calculated the density of water. So that's what you were measuring. Now, number 9 says, okay. What did you get for 8? Oh, that's pretty good. Okay. Now, number 9 says, calculate your experimental error. I'm going to write what experimental error is on the board. Okay? Can y'all see from everywhere? Okay? Experimental error. Y'all watching?
Yes.
Okay. In the back. Experimental error is measured minus actual. Is that right? Yes. Because if measured too big, that's a positive experimental error. If measured too small, it's a negative experimental error. So your experimental error is measured minus actual. The measured is what you came up with. The actual is 1.0. Second. 1.0 is. Okay, I'm sorry. We're on number 9 on the back. You got 0.95. So then your experimental error is the measuring is 1.95 minus 1.0. All right. There was a very legitimate question there, and that was going back to the ratios of diameters to circumference, or circumference to diameter. Did y'all do that experimental error? I know, but also.
Get the experimental air.
Now, there was a question, a very legitimate question, and this is going back. Hey, did everyone do all your ratios of circumference to diameter? Everybody got it? Did you take those 9 measures, 9 ratios, add them together, and divide by 9? What did you get as your average C to D? Someone has a question. Okay, you do the ratio of circumference to diameter, and this divided by that. This divided by that. You get all those done, add them up, divide by 9, then your answer. That's where I'm in. Someone said,
Yeah, CD part. I'm redoing it right now.
Round off very far, didn't you? But it's okay. You said all those were the same. Huh? Oh, this is really suspicious that all those are exactly the same. Huh? Okay. Well, anyway, add these up, divide by 9. That gives you a number. And then I'll tell you what to do. Yeah. What's that?
Yeah, some of them will vary.
Oh yeah, you better have variation. Otherwise,
Some of them I went more pedestrian.
Yeah. That is really suspicious. 3 different people taking the measurements exactly the same. All 3. Huh? Huh? Right. Okay, but the thing is, if you all drill differently, I can't see how you got precisely the same. Right. Okay, but that was supposed to represent that. I'm gonna say, okay, but you all measured them separately, and you all got precisely the same measurement. That's max. But I mean, you've done it. It's done. Okay. Now, you don't have this right. It says ratio of C to D. That C is so, yeah, you had some variation.
I'm just doing one. Whoa!
Average those together. Is that what you got?
Yes.
That's your measure. What's the actual? You know what it is?
Where's the actual?
Yeah, we do. Just write something down. Ready? Look, right. Yes. Okay, very good. So that again is the negative. Right, okay. That's what I was just gonna get to because it's running up. Okay, yeah, well, that's what I'm gonna get to. Oh, we still got 15 minutes though. Okay. All right. Now, I just want to get a reading from y'all. Okay? Just to get how you're doing. Let's go back to your original things, your circles. Okay? Did everybody? I hope you got your measurements. Did all of you do your ratios? Okay? Just give me a sample of one of those ratios. Okay? 3 point something another. Did everybody have a ratio of about 3 point something? Something close to that. I saw at least one paper that had a 0.3. That tells me they divided wrong. Okay, so make sure it's 3 point something or something close to that. Definitely not a 0.3 or something close to that. Okay? Once you get those ratios done, then add the 9 ratios together, divide by 9, that will be your average ratio, right? Now, what is that supposed to be close to? What is pi? And what is pi? 3.14. So that's what you determine your experimental error from, whatever you do. Average is, just like there, your measure is your average, subtract from it the actual pi. See what you get. Okay? Now, did everyone get your measurements on the small, medium, and large cubes, set surface area, and volume? Then your calculation was the ratio of an area to volume. Okay? And write those down. Now, when you get that done, you go back and answer question number 6 on page 16. Don't forget to do that. Okay? Then you do what we've been doing so far, and that's your 8, 9, 10, and 11. Now you can hold off on 11 if you want to, but don't forget to go back and do it. Here's why this lab is the longest and most complicated of all the labs. They have a bunch of result questions as well. And these result questions are on page, and some of this you can get from the reading you did, others you get from what you did in the lab. So that's page 19 and the top of 20. And then after that, you have some problems. And this is the only lab with problems. This problem is this aluminum block. They show a picture of it here, and those are measured in meters, and then you answer those questions from that. So then you go from that, and that wraps it up. So you should have every question answered. Now, I bet you y'all haven't gotten to the results and problems, have you? No. Do you want to try to do those on your own or do them in class next time? Okay?
Green doesn't
anything you put there is counted okay. If you didn't think it was accomplished, you gave a reason, that's okay. That's a complete. Okay, I'm going to turn off this.